City University of Vietnam from Vietnam. Come to the conference today, I would like to discuss my research about the screen control based on the Locus technique for exploratory cycle of tunable acting speeds from good ventilator. And from now on, we call the tunable acting Piston TABP. Yeah, for briefing. We have total 5 sessions for discussing today. So I would like to go over this briefly. As you know, the COVID-19 pandemic in the 2019 raised the need for the greater intensive care and mechanical ventilation capacity around the world to respond to the emergency medical in the future. While high-income country has sufficient standard ventilator supply, but the low and middle-income countries still face significant shortage and limited access to critical care surgery. So now some non-governmental organizations start to design the medical ventilator for the low and middle-income country, and there are some 3 requirements for this type of the machine. It's like the first is multiple simple, and second they must be low cost, and finally, and yeah, they must be fast manufacturing, especially in some medical emergency. And nowadays, the mechanical ventilator automatically have numerous modes, range from similar to complex. But generally, they continuously monitoring the 3 main variables: is airflow, pressure, and volume, and adjust the control signal to maintain and to the pattern needs. And so, if the controller of the ventilator do not control design accurately, this may be led to some dangerous for the partners or for the health. So this paper, so I want to focus on design VD controller based on the rule Locus. Yeah. And the ventilator mode that I focus on the mandatory volume control mode. And in the mandatory volume control mode, they want to control the airflow of the ventilator, which acts according to the square waveform, as you can see in the second green graph. Yeah, and to reach the tidal volume at the end of inspiratory cycle. Inspiratory cycle is at this point to reach the tidal volume here. And the amplitude of the square flow will be calculated according to the equation 1. And this is the overall control structure, and I will relate the patterns learned by the test learned. And with model, I can easily adjust the airway resistance and compliance for the different clinical scenario. And in this mode, I use one proximal flow sensor and one pressure sensor, and feedback to the controller, and starting the control signal to the DABP system. This is the principal mechanical of the DABP. You know, there are 2 wisdom with they are 90-degree phase and move up, move down, and suck the air to the inlet spot and move the air to the outlet spot here. Yeah, this is the transfer function of the DABP system. It ranges domain with the output in the airflow and input in water supply to the air receiver, range from the 0 to 5 volts. As you know, as you can see, the overload system, when you without any controller, you can see although it's stable, but can track to the design reference. So we need a controller for it. And controller performance will be evaluated in 3 scenarios: is normal, COPD as chronic obstructive pulmonary disease, and ARDS stands for acute respiratory distress syndrome. And there's some performance criteria, and the controller will be designed in the discrete domain with the simultaneity with zero audible. Yeah, and from the overshoot at standard time, we can calculate the damping ratio and natural frequency. And yeah, from that we calculate the nominal code spare Z star. And this use the Z transform for the closed loop system. You can see this is like a P controller. You can see the design goes for in the red here, but the Locus never goes through this point, so we need to design a more suitable controller, not only a P controller. Yeah, this I will briefly go over this part. Is the transfer function of the PD controller in the frequency domain with the 10S. What's called 10S0 and 10S2, and you can see the compensation angle if we start is equal to the 25.69 degree. And from this regular compensation angle, you can determine the position of the Z2 is equal to the 0.4. And again, K1 will be determined from those conditions, and we have the KB, KD. And as you can see, the Piston response is true, but have some satisfactory error. But then we need to one step in add an integrator for this controller. And the BI controller integrates discrete domain in like 11. And to maintain the present response of the BE controller that I mentioned before, we choose the Z2 is very close to the pole Z actual 1. And the K1, if we recalculate, we will have K2 be very, very approximately to 1. And we have the Ki and Kb. Yeah, after we design have P, I, and D controller. But it's not just a preliminary parameters. Yeah. It's the after integrator, the transfer response is maintained and it's eliminated error. And the Locus, you can see, is go through the disciples. And its experiment, I will assume that we will apply to the patterns with the system on male and have the height of 160 centimeters. And from that, we can calculate the IBW. The ID body weight is equal to the 66 kilogram. And from the ID body weight, we have some appropriate ventilator testing for different scenarios for normal lungs. For COPD, you have a higher resistance, and on ICACE have a smaller complex. And we will apply the discrete control law into the microcontroller. And this is the normal waveform. In normal waveform, we don't have any injury in the lung, but in another part of the body, such as head injury, cardiac arrest, post-operative, and so on. This is the COPD. The COPD will have a higher resistance in the airway of the buttons. Like we maybe have accumulation and breathing difficulties. And so we must have lower the tidal volume than the breathers for, and we must extend the respiratory time to have enough time for the air to expel the blood. And the ARDS, you can see, is have a normal resistance but smaller compliance, so the lung will difficult to extend. So and it will collapse quickly. So we don't need to attend the exploring time, but we need to attend the exploring time to train the gas exchange in the lungs. Yeah, this is the experiment in the normal lung scenario. Yeah, you can see this flow waveform that I control. And you, as you mentioned before, the output of the DMPB system will not stable curves. It's all half waveform. This will break. So the flow that I control is average value of the airflow. Yeah, and in this experiment, I set the peak is 5 centimeter water, and I'm sorry. Do I how much time?
1 phút.
30 seconds.
1 phút nữa, 1 phút.
Yeah. And so we have a large exploring time. And the areas we have some problem with the problem because the advantage of the beam is mechanical vent. So it will be vibrate when it has hold the lungs, and so it will cause some noise in the flow sensor, so led to the fail in the reduce in the volume. You can see it's not reach the zero, although the talent is completely correct. And this also see the phenomenon that I discussed previous is the autobeat. Autobeat is the phenomenon that's when the air is pressure into the lungs have not yet reached the peak pressure, but have another amount of air right into the lung, and then which will and the lung will be larger and larger, and the pressure will be go up, and it's not just enough safety for the patient, and the doctor must have some interventions in this case to maybe extend the exploratory time or between the airflow or between the tidal group and so on. And this is another the version of the Locus ventilator. It has more advantage in the previous version. That's the output airflow of the system is more stable than the previous one. As you can see, it's quite linear with the angle of the river, because it's just a little bit not linear in the present that it's a contact the bone. Yeah, it have not reached the maximum contact. It would be a little bit non-linear. And in this experiment, I have controlled another type of the flow waveform in the sim waveform, but in this completely square waveform. So achievement, additional compensator significantly improve transfer response and steady state of output compared to the original system, and the experimental result and simulation result. You can see the tidal volume is below the 10%, and this is a low to the standard according to the DCBM about the ventilator verification. And the limitation is that the control parameter in each ventilation therapy is just keep a constant and the vibration and instability of the big fan cause the unexpected noise in the flow sensor. You can see it's not return a good result in the ARDS scenario. And so to work, we will have apply the adaptive PD controller or maybe a repetitive control for auto-tuning the controller parameter while while the machine is operating. Because the height, as you can see, the resistance and the airway compliance, this can be changed in this. And so if the control parameter is constrained, it's not reached optimal performance. And the second, I will replace the manifold bit fan with a control exploratory fan, which is a solenoid fan, to eliminate the disadvantage of the vibration with a high frequency of shift spring. And the final is the most important is a calibrated machine. Although you can see the channel volume is barely below 10%, but I don't know how much the volume that I put to the output. So I noticed the standard device to calibrate my machine. It's the end of my presentation. Thank you both.
Thank you for your very interesting presentation. So, if you have any questions for you, please raise your hand. If you don't have, so I have one comment and a question. Can you move to slide 27? Okay.
27.
Yes.
27.
This is the actual, that means the simulation result. Reference is the reference point.
It's
I think you should change to the reference result. The actual, that means the experimental. So I see from this one, the performance and control is very good, right? But the thing is, in the control system, we not only consider the accuracy, but we also consider the control cost, control energy.
It's about the control signal.
Yes. So because sometimes even the result is very good, but we make the adjustment or sometimes the control energy very high. So it's very hard to apply to the reality, right? So in this case, did you investigate the control energy of your system?
In this study we don't have any the image in here, but as you mentioned, the airflow in the halfway you can see it's like mountain. It's very so we can feedback the very much noise signal to the controller. Which will counteract the chattering in the control signal to the motor. So when there's a solution for it, we can use a filter to average the output airflow equal to the average of the output of the general function, and we will compare if we will integrate the airflow and see if the filter that I use is effect to the channel volume when after I integrated it, and I see it it's different much. It's only 2 to 3 millimeter, and it's safety to the adapter. So I use the average filter, moving average filter, to filter the average signal and feedback to the design phone, and it will eliminate this chattering in control signal.
So also, ICACE is good. You use the filtering, right?
Filtering. But I don't.
Another thing, like this, they are showing the conclusion. You can do the adaptation mechanism for your system for turning the control parameter. Then you can also optimize the control cost.
Yeah. Thank you
Okay,
for
so in general, it's presentation is very good. You have the very clear and very interesting result.
yeah.
Thank you so much. So now I would like to deliver the